Enantiomers are defined as molecules that are mirror images of one another, but not superimposable. So to get some idea of superimposable mirror images, let's think about shoes and socks. I have a pair of socks. They're mirror images of one another, and they're superimposable. They look the same, and it doesn't matter which one I put on my right foot and which one I put on my left foot. They both work. They are identical. Now let's think about shoes. Okay, I have a right shoe and a left shoe. They're mirror images of one another. And if you're having trouble seeing that, next time you're in front of a mirror, put your right shoe in front of it. What you see in the mirror is an image of your left shoe. The point is that these are not superimposable upon one another. Okay, I can't put my right shoe on my left foot. It doesn't work. They have a handedness to them. These are not identical. Where this image of mirror images that are not superimposable comes into play in chemistry is when I have a carbon, tetrahedral carbon, with 4 different groups around it. Got this carbon in the middle with a white atom up, a red one in front, a blue one in back, and an orange off to the left. And here is its mirror image. Now, these 2 molecules are not superimposable. The atoms actually are in a different orientation in 3-dimensional space. And if I try to superimpose them, well, I can superimpose the white and the red. Okay, I can get them to match up, but, oh, now orange and blue don't match up, do they? What if I tried to superimpose the red and the blue? Okay, I can get red and blue, the 2 blues together, the 2 reds together. Oh, but now orange and white have traded places. No matter how I do this, I can't get them to superimpose upon one another. In fact, I have 2 different isomers of this molecule, and we call those isomers enantiomers. Where the importance of enantiomers is seen is in biochemistry. For example, humans use what are called L-amino acids. If we look at the 3-dimensional structures of amino acids, there is a carbon in the center with 4 different groups coming off of it: an NH2, a COOH, an H, and an R, which is called the side chain. Different amino acids, and you use 20 of them, have different R groups or side chains. But notice the 3-dimensional shape of the molecule. In the L version, the hydrogen is coming out toward us, whereas in the D version, the R group is coming out toward us. Interestingly enough, our bodies only use the L version and not the D version. The 3-dimensional disposition around carbons that have 4 different groups around them can affect the biological activity. Something as simple as our sense of smell can be sensitive to this. The carbon highlighted in red in the molecule carvone has 4 different things around it. That carbon is sometimes called a stereocenter. These 2 structures are mirror images of one another, but have different smells, one giving the odor of caraway and the other the odor of spearmint. One of the most notorious examples of the different biological activity of enantiomers is in the case of thalidomide. This drug was introduced to pregnant women in the late 1950s and early 1960s for its anti-nausea activity to combat morning sickness. What wasn't known is that only one of the 2 enantiomers has that activity. The other enantiomer causes severe birth defects, and upwards of 10,000 children were born with birth defects, mainly malformed limbs. Thalidomide has made a comeback, not as an anti-nausea drug, but as a chemotherapy agent for people who have multiple myeloma, or cancer of the white blood cells. It's hard to believe that simply switching the location of 2 chemical groups in 3-dimensional space has such a profound impact on the biological activity of a compound.